Mwalimu Teofili Academy reminds you that success is not an overnight process, but consistency. Welcome for today's session.
Example 3 states that calculate the mass of magnesium metal that will be produced during electrolysis of molten magnesium chloride if a current of 1.93 ampere is passed through for 16 minutes and 40 seconds. You are also given the relative atomic mass of magnesium is 24 and of chlorine is 35.5. Now, let us see the solution for this question. Here, let us first analyze the data which we have. Now, solution. Data given. The data given here, we are given the current, electric current I. We are given that it is 1.93 ampere. Another data we are given is time T. Time T we are given is 60 minutes and 40 seconds. So this is 16 minutes and 40 seconds. When you convert the minutes into seconds, you're going to have 16 minutes times 60. Now this will be in 2 seconds, and the answer obtained is going to be added with 40. It's going to be added to 40. Those, all of them will be in terms of seconds. When you multiply this, you're going to get 960 plus 40. This will be equal to 1000 seconds. 1000 seconds. So this is the given time. Also, we are given the relative atomic masses of magnesium and chlorine. So what is required here to calculate the mass of magnesium deposited, magnesium metal? Mass M of magnesium. Mass M of magnesium deposited on cathode. Deposited at cathode. Is equal to how much? So the task is to find the mass which will be deposited when the current of 1.93 ampere is passed through that electrolyte within 1000 seconds. Now, to calculate this by using directly the data given, let us use the balanced chemical equation, which shows the reduction of magnesium ion into magnesium metal. Now, there is this reaction at cathode. Reaction at cathode will be the magnesium ion. Magnesium ion is going to be reduced by gaining 2 electrons and becomes magnesium metal. As you see it here, it becomes magnesium metal. So from this balanced chemical equation, we can use the idea of mole concept and stoichiometry so as to know the mass of magnesium which will be deposited. Now, from this equation, 2 moles of electrons are required so as to deposit 1 mole of magnesium. 1 mole of magnesium. Now, this is the details from the standard balanced chemical equation. So from these details, now let us relate them with the given data. The given data, we have time and current. So time and current are enough to give us the electric charge in terms of coulombs. So if they give us the electric charge in terms of coulombs, let us even the data we have from the standard equation be changed in that direction. So here we are going to convert these 2 moles of electrons into charge. So here we say that 2 moles of electrons are equivalent to 2 Faradays. This is true, that the number of moles are equivalent to the number of Faradays. So instead of writing 2 moles of electrons, I'm going to write 2 Faradays. Also, you have to know 1 mole of magnesium is equivalent to 24 gram per mole. I can say 24 gram. So you have also to know that 1 mole of magnesium is equivalent to 24 gram. Oh, now in place of 1 mole of magnesium, I'm going to put 24 gram, and in place of 2 moles of electrons, I'm going to put 2 Faradays. So here, why I have started changing this into Faradays and gram? This is to match with the data which we have. In the question, we are asking to find the mass. So these given moles of magnesium should be changed into mass so as to simplify the road for us to get the required mass. Also, I have changed the electrons into Faradays, as the Faradays are going finally to be changed into charge, I mean in form of coulombs. So here, instead of writing this, I can use this data. So it will be 2 Faradays are equivalent. 2 Faradays are equivalent to 24 gram of magnesium. It becomes this way. Now, what is next? Here, let us change the Faradays into coulombs, I mean to charge. It will be 1 Faraday is equal to 96,500 coulombs. So instead of writing Faradays, I am putting 2 times 96,500 coulombs. So 2 times 96,500 coulombs is equal to 2 Faradays. Now this will be equal to equivalent to 24 gram of magnesium. 24 gram of magnesium. After that, now we are in the position of being able to compare this equation with the given data. Now, in the left-hand side, you have coulombs, and as we are given time and current, we can change this into coulombs, to charge. As you know, to get charge is equal to current times time. So it means that when I take 1.93 ampere times 1,000 seconds, these are equivalent to the mass which will be produced and which is not known as it is asked in the question. So will be equivalent to M, mass of magnesium, which is to be calculated. As this mass will depend on the current applied within a given time. So here, how are we going to get this mass of magnesium? How are we going to get this mass of magnesium? We are going to get it by crossing multiplication. By crossing multiplication, we are going to get 2 times 96,500 times M, this mass, is equal to this value times this. So it will be 1.93 times 1,000 times 24. It will be this way, it will look this way. Now, how can I get mass? Let us first multiply the values which are on each side. Here we have, on the left hand side, we have 2 times 96,500. Here it brings 193,000 M, as M is not known, is equal to 1.93 times 1,000 times 24. Here you get 46,320. So what next here? What next here is to get the value of M. So to obtain the value of M, you are going to divide by 193,000 both sides. So here we have 193,000. M is equal to 46,320. So you divide by 193 both sides. 193,000 both sides. Here we're going to remain with the M. So the value of M will be equal to 46,320 over 193,000. You have to know that this is mass, so it will be in gram. It will be in gram. Let us now divide. Now let us divide. We are going to divide 46,320 over 193,000. What do we get? The answer here becomes 0.24. Becomes 0.24 gram. So this is the mass of magnesium which will be deposited at cathode. This is the mass of magnesium to be deposited at cathode. Apart from using this, we may use an alternative. Alternatively, we say that alternatively we may use the formula according to Faraday's first law of electrolysis. That the formula say that mass is equal to ZIT. It means that mass deposited is equal to electrochemical equivalent times current times time. In this equation, to get this mass, you must have these all three data, but we are only having two. We have current and time, and we are not given the electrochemical equivalent of magnesium. To calculate the electrochemical equivalent, to calculate Z, I told you that, well, we are told that to calculate the electrochemical equivalent of any element is equal to relative atomic mass over valence times Faraday's constant. So for magnesium, if we are looking for magnesium, the value of electrochemical equivalent will be equal to its relative atomic mass. The relative atomic mass of magnesium is 24 gram. Now you take 24, you divide by its valence. The valence of magnesium is 2 times the Faraday's constant is 96,500. After getting this electrochemical equivalent of magnesium, now we are able to compute it in this formula so as to get mass. Now we get our mass will be equal to electrochemical equivalent, which is 24 over 2 times 96, 2 times 96,500. 96,500. After there, this is electrochemical equivalent, which is indicated as I said. We multiply with current. What current do we have? The current we are given is 1.3. The current we have is 1.93 ampere times the time given. The time given here is 1,000 seconds. 1,000 seconds. So here the answer obtained from this is in terms of gram, as we are looking for the mass. Now what will be the answer? Let us compute it into our calculator here. We have 24 times 1.93 times 1,000 over 2 times 96,500. The answer here becomes 0.24 gram. So the answer is the same as what you obtained in the first solving. So here conclude the mass of magnesium deposited at cathode was 0.24 gram. was 0.24 gram. This is the answer for our question. This is the answer for this third example, and I hope the competence for you, I hope your competence is increasing now on the way to tackle different problems concerning with the Faraday's first law of electrolysis. Let us see our fourth example.